Hello and welcome to this Isabellenhütte webinar. My name is Matthew and I will be your Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today's session. Just to the right of the main presentation window is the Speaker Bio window with background information on today's presenter. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now let me introduce today's presenter. With us today is Matthias Hilpert, the Sales Director for Precision Measurement at Isabellenhütte, USA. To read more about Matthias, please look at the Speaker Bio window right next to the main presentation window. Matthias, welcome to today's event. With that, I will pass things along to you to get started.
Hello and welcome to the Isabellenhütte Precision Measurement Systems webinar. Smart Sensing Considering the Functional Safety Aspect in High Voltage Battery Systems. In this webinar, we'll cover mainly three topics. Functional safety for high voltage battery systems. This will include an overview of the ISO 26262 requirements for smart sensing in these high voltage battery packs. We'll cover a little bit of isolation monitoring, especially the differences between active and passive isolation monitoring. And then we look into the placement of voltage sensing points for active isolation monitoring. Lastly, we'll wrap up the takeaways from this webinar and we'll have a look into solutions that are available to cover smart sensing needs in high voltage battery packs. First, I would like to start off with a little bit of an introduction of Isabellenhütte company. Isabellenhütte makes roughly $200 million dollars of turnover every year. It is a German company headquartered in Dillenburg, which is right in the heart of Germany in Hesse. We currently have around 1,000 people employed worldwide, and we do have subsidiaries in the United States, in Massachusetts, in Japan, and in China. Isabellenhütte is actually one of the oldest companies in Europe. It was first founded in the year 1482, first mentioned in the document back then, and it started off as a copper smelter. Today, we're a global leader across three business units, which are precision alloys, precision and power resistors, and precision measurement. In precision alloys, we don't do copper anymore, but we do thermoelectric and resistive alloys. And from these alloys, we actually produce our power resistors, our shunt resistors. So we have a very deep vertical integration in this company. We offer surface mount and busbar mount precision resistors. And the third business unit we have is precision measurement systems. So basically, from our precision resistors, we build up what we call smart sensing modules, which are mainly current sensors that use the shunt resistors that we produce. And then we add different functionality like voltage sensing in some cases or isolation monitoring. And these modules typically communicate through a CAN interface and are fully temperature compensated over lifetime. That's why we call them smart modules. So within the business unit of precision measurement, we had a lot of thoughts about priorities and challenges that our customers actually face. And we talked to a lot of customers and collected some of the key items that we think are important for our customers. We talked about business objectives, technical objectives, and obstacles that our customers face and they want to overcome. As far as business objectives go, While everybody wants to improve their profitability, they want to create reliable products and systems that work well for their customers, and they want to establish and increase their customer loyalty. As far as technical objectives go, they want to establish technological leadership, or at least they want to have some kind of competitive advantages over their competitors. They want to optimize their products and systems for multiple use cases. For example, if one customer is mostly active in automotive, they may want to adapt their product also for application in industrial environments. And they want to leverage modularity for maximum flexibility, means they want to be ready for future applications and have modular products that can be adapted without incurring high costs. As far as obstacles go, adding functionality usually raises cost, and that's an obstacle that they want to overcome. And there's always new requirements for new functions that need to be implemented. BMS architecture is increasingly complex, so there's new standards out there that need to be fulfilled. There's the whole functional safety requirement out there. So this is an obstacle that a lot of our customers talk about. And last but not least, there's electromagnetic influence that is still present, and they are looking for methods to provide products that are coping well with electromagnetic fields and can easily be applied in environments with strong conductors around them. We will talk about these challenges and obstacles, in particular in high voltage systems and the area of smart sensing, over this webinar and through this presentation. And then at the end, we will look at these business objectives, technical objectives, and obstacles again, and we will actually see what kind of solutions are out there in the market that can actually be used to overcome these. Now we want to talk a little bit about functional safety, especially the requirements in high voltage battery pack systems according to ISO 26262, and also especially geared towards current and voltage sensing systems. ISO 26262 was developed with the help of the automotive industry, and it replaces the old IEC 61508 as the functional safety standard for street vehicles. Having said that, it can also be used for commercial vehicles though, and we can see a trend in the industry that this is more and more the case. ISO 26262 is a vast standard of more than 500 pages, so it covers really all the steps from the concept phase through production, and even beyond that, companies have to establish a whole functional safety department almost in their companies to comply with this standard. The goal of this functional safety standard is to reduce product liability for OEMs. It is based on the principle of vehicle OEMs' road safety obligation. So in other words, it's supposed to help OEMs to produce safe vehicles for their customers. ISO 26262 is also often described and explained as the so-called V model. First, there's the so-called higher order processes, like the vocabulary definition and also the management functions of functional safety, like for instance, the overall safety management. Next, there's the core process consisting of the concept phase, the product development phase, and the production phase. That can also be described as a V-shaped cyclic process. Starting off on a high level in the concept phase and the product development phase, The whole process breaks down in the system design phase, where it splits up to the hardware level product development and the software level product development. And these processes can run simultaneously and in a cyclic manner. After that, the process integrates back up to system level, where item integration and testing occurs, and later the release for production. Next, there's supporting processes like change management and documentation, and ASIL analysis, like, for example, failure analysis. Now, to understand how ISO 26262 can be applied to smart sensing in high voltage battery systems, we want to pick one subphase of the concept phase, hazard analysis and risk assessment, to dive a little bit deeper and look at that in a little more detail on the next slide. Every OEM and battery manufacturer needs to go through hazard analysis, where they determine severity, exposure, and controllability of hazards in order to avoid accidents like car or battery fires. Here's an example of what a hazard analysis can look like for a smart sensing module in a high voltage battery system on a very high level. The simplified spreadsheet below shows possible component failures in certain situations that have certain hazard scenarios as a result, and the severity, exposure, and controllability evaluation that results in a certain ASIL rating. A failure of the current sensor, for instance, can cause overcharging of the battery. This situation can occur during charging, while the vehicle is in stop but with the ignition on, or during driving in recuperation mode. The resulting hazard here is smoke and fire from the high voltage battery system due to overvoltage. A possible evaluation of severity, exposure, and controllability could be that this can result in fatal injury. It's possible to control during the situations of charging and stop. A current sensor failure has a large impact on the state of charge as well. While the vehicle is moving, this whole situation is also difficult to control. The resulting ASIL level evaluation will be ASIL level A for the situations charging and stop, and ASIL level C for the situation driving. A different component failure would be the failure of the isolation monitor. This failure could cause a loss of information on the isolation status. Also, this situation could occur in charging mode or while charging, and also during driving. The resulting hazard here could be electric shock due to contact, exposure to high voltage parts due to aging components. In all situations, these hazard scenarios can result in fatal injury or death, but the failure of the isolation monitor doesn't directly cause an isolation failure. It's just a loss of the info on the isolation status. That's why in that case, the ASIL rating that was derived from this was B. Other component failures, like the failure of a voltage sensor, can be evaluated in a very similar manner. Now let's have a closer look into how these ASIL levels are actually defined. The abbreviation ASIL, or short ASIL, stands for Automotive Safety Integrity Levels. They are determined according to fixed methods defined in the standard through the parameters exposure, controllability, and severity, as we've seen in the example of hazard analysis on the last slide. There are 4 ASIL levels, A through D, with D being the highest level. And then there's an ASIL QM rating for non-safety relevant parts. Below you can see another example of a hardware design safety analysis. The proposed content here is a deductive analysis and an inductive analysis. And you can see that depending on the ASIL level that is supposed to be achieved, there's different levels of detail that have to be performed. The higher the rating, the more detail is required, or in other words, the more explanation is necessary if the analysis listed here is omitted. The lowest level is 0 and the highest level is ++. There's one important comment that has to be made. These parameters leave quite some room for interpretation. Nevertheless, to have an international framework of rules is necessary, so the OEMs have some kind of regulation they can stick to. Now we want to look a little bit closer into the isolation monitoring topic in high voltage battery systems. Especially, we want to compare active versus passive isolation monitoring methods. Isolation monitoring systems in electric vehicles are used to monitor the isolation between the electric vehicle high side, means the high voltage battery, and the inverter, the motor, the drivetrain of the electric vehicle, as well as some auxiliary components like the heater and the AC unit, which are shown in red in this block diagram, and the 12-volt side of the electric vehicle, which is shown in green and includes the communication line like the CAN bus, for instance, and other control units, as well as the 12-volt battery. Now, it is important to monitor this isolation between the high side and the low side for safety reasons, as obviously the vehicle has an interface with humans, and humans touch metal parts of the vehicle which serve as the ground side of the 12-volt system. So if there's a leak between the high side and the low side of the electric vehicle, that can represent a hazard for humans interacting with the vehicle. So that's why it's important that we constantly monitor the isolation level between the high side and the low side of the electric vehicle. In the recent years, a lot of different isolation measuring methods have emerged, but the basic 3 are described here. The UG method, which is an unsymmetrical voltage-to-ground measurement method, was invented in the 1970s. UG is still used today, but not allowed in newer EV standards anymore. However, some countries like China still allow to use it. The 3VM method, or 3-voltmeter method, is also a passive measurement method and can still be used. It is able to detect symmetrical errors, and we will look a little bit closer into that on the next slide, what that means. The active measurement pulse method, or AMP method, works with unenergized bus systems and can also detect symmetrical as well as unsymmetrical isolation errors. Coupling methods for all 3 isolation measurement methods can be either resistive, capacitive, or inductive. However, resistive coupling is used the most frequent. When choosing an isolation monitoring system, we have to decide what fault we want to detect. An unsymmetrical fault or a symmetrical fault. Symmetrical faults can occur due to aging or corrosion on contacts. Unbalanced errors are more frequent and typically occur due to a component failure or a short in the system. The UG measurement method is able to detect unbalanced errors only, while the 3VM measurement method as well as the active measurement method can detect both symmetrical faults and unbalanced errors. Now we want to look at the difference between unsymmetrical and symmetrical errors in high voltage battery systems. First, we want to look at a normal state in a high voltage battery system. You can see that the coupling resistances, both from the positive pole and the negative pole of the battery to ground, are at 5 mega ohms. So there's no isolation fault in the system. An unsymmetrical fault would cause to drop one coupling resistance either on the positive or the negative pole of the battery further than the other. In this case, our resistance from the positive pole of the battery is still at 5 mega ohms, so there doesn't seem to be a fault here. But the coupling resistance from the negative pole of the battery to ground is at 10 kilo ohms, so there is some isolation fault here. That means there's a difference in the coupling resistances between the positive and the negative pole, which causes the isolation voltage to drop to 0 volts on the negative pole, and the full isolation voltage is measured from the positive pole to ground. In case there's no error in the system, the coupling resistances both from the positive pole and the negative pole to ground is 1/2 of the total voltage. Now let's look at what a symmetrical fault in a high voltage battery system would look like. Still on the left side we see the normal state with no isolation error. On the right side we have simulated a symmetrical fault in our high voltage system. In that case, both coupling resistances between the positive battery side and chassis ground, as well as the negative battery side and chassis ground, dropped to 50 kilo ohms. Now, what does that mean to the measured isolation voltages? You would still measure 1/2 of the isolation voltage from the positive and the negative pole of the high voltage battery to ground. So, despite the presence of an isolation fault, there is no voltage shift to be detected when a symmetrical fault occurs. Finally, let's summarize the pros and cons of the 3 isolation measurement methods that we looked at. First, the UG method. The UG method has a fast reaction time and it's a very simple structure, so it's very simple to design, and it has comparably low cost to implement. However, with the UG method, you can detect symmetrical errors, and monitoring of a non-energized bus is not possible. Second, the 3 voltmeter or 3VM method. While it has good precision under stable conditions and recognizes symmetrical errors in comparison to the UG method, it still has very high tolerances in unstable conditions, and it has significantly longer measurement times than the UG method, and also with the 3VM method, there's no monitoring at a non-energized bus. Lastly, there's the active isolation monitoring. The active isolation monitoring features excellent precision and it can recognize symmetrical errors. Also, it's a very robust measurement method if you look at noise and voltage drops. Apart from that, it also doesn't require an energized high voltage network, means it can measure at a 0-volt high voltage. The measurement times are still longer though than these of the UG method, approximately like the 3-voltmeter method measurement times. Now let's pick the active isolation monitoring method and look at how we would place our voltage sensing points in a high voltage battery system to get the best possible readings for our active isolation measurement system. Now this diagram shows a simplified high voltage battery system circuit here. And I first want to start with going over this diagram and explain a little bit the content. So on the left side here, we have the chassis side, so the low side of this battery system or the vehicle that also extends down here. And it's basically important for our reference point to chassis ground. Then we have the DC pack side of the high voltage system on this side and the DC link circuitry on the right side of this diagram. Now next, I want to walk through the different components real quick in this diagram, just so we are on the same page what we look at here. So on the positive side of the battery, we have the fuse, the main fuse on the positive side. Then we have the pre-charge circuitry right here with the relay on the positive side and the pre-charge relay as well as the pre-charge resistance. Next, we have the DC link capacitance and DC link circuitry, and then all the way on the right here, the inverter circuitry and the drivetrain. On the negative leg of the battery, we have the relay on the negative side as well as the fuse on the negative side. Next, there's three different things I want to go over with you in this diagram. First, it's the placement of our high voltage sensing points for our active isolation monitoring in the circuit. Next, I want to go over the isolation resistance results that we actually get from the placement of these sensing points. And last, I want to go over the results in dependence of the state of the fuse and the relays of our isolation monitoring system. So let's start with the sensing points in our system. So in this case, our reference point is on the negative leg of the battery. If it was on the positive leg of the battery, our first voltage sensing point, which is the battery pack voltage, would be placed on the opposite side. From our reference point, or the point where our isolation monitoring system is located, we also need a sensing line to chassis ground, to the low side. The next sensing point that we would set is on the positive DC link side of the circuit, and also one on the negative side of the DC link circuit. So 3 voltage sensing points in total that are marked as red dots in this diagram. Next, we want to look at the isolation resistance monitoring results that we would get from this. So we would get a total isolation error plus minus from the pack and from the link side. So a combined calculation of our active isolation monitoring system from all the 4 different sensing points that we have in the system. And then we would get the dedicated isolation errors on the pack plus and minus side, as well as on the link plus and minus side. Now let's look at how the results would look like in dependence of the state of our fuse and our relays in that system. So the main fuse has to be closed always for us to get some reading. But if we have all our relays, so the pre-charge relay, the main relay plus, and the main relay minus open, the state of the isolation monitoring would be disconnected, and we would get no total isolation reading in that case, but we would get a dedicated link isolation and pack isolation reading. In case the pre-charge circuit relay is open, but the main relay on the plus side is closed, and also the main relay on the minus side is closed, the isolation status would be connected, and we would get a reading of the total isolation voltage, positive and negative to ground. If the pre-charge relay is closed, on the other hand, but the main relay on the plus side is open and the main relay on the minus side is closed, the isolation state would be pre-charge because the pre-charge circuitry is active. In that case, we would get also a reading of the total isolation voltage, positive and negative. And the last case we would get a reading is if pre-charge relay is closed, main relay plus and minus are both closed, so the whole circuitry is closed, which would again be the state connected, and we would get a total isolation reading, positive and negative. Now that we've learned about some aspects of smart sensing under functional safety aspects, now let's wrap up things and see how we can actually face our challenges with possible solutions and the things we need to tackle this topic. Now, we looked at this slide at the beginning of this presentation, and now that we learned about some aspects of smart sensing under functional safety aspects, we want to look at how better measurement technology can help you overcome your challenges and help with your priorities. With regards to your business objective, it's important for you to improve profitability and create reliable products and systems. You want to reduce system cost, and you want to have ASIL certification of your smart sensor to increase flexibility of the application. You also want to choose a reliable partner. With regards to technical objectives, it's important to establish technological leadership and to optimize your products or systems for multiple use cases. To do that, you want highest accuracy of your current and voltage measurement system, and you want a modular system with a low power loss. Lastly, with regards to the obstacles that you want to overcome, adding functionality almost always raises cost, and as we learned, the BMS architecture is getting increasingly complex. So important items here are price reduction, a reliable isolation monitoring method to achieve high EMC levels with your smart sensor, and a compact design of the sensing module. So if you agree, you need to optimize your products for functional safety compliance, achieve ASIL-rated current and voltage sensing capabilities, reliably monitor your isolation voltage in your high voltage system. There's good news because there are solutions out there that can help you, that are affordable, accurate, durable, and compact, and that provide current sensing, voltage sensing, and active isolation monitoring functionality, that are fully ASIL-rated, and that have different CAN interface options available. Thank you very much for joining our webinar about smart sensing under functional safety aspects. My name is Matthias Hilpert, and we'll start with our Q&A session now, but also please feel free to reach out to me after the webinar in case there are any follow-up questions.
Thank you so much for that great presentation. Now we're going to move into the Q&A. We do have some questions that have come in from the attendees, so we're going to move into answering those right now. If we don't get to your question, don't worry, we will have an answer for you following the webinar. And if you haven't submitted your question yet, you can still do so now by entering it in the Q&A box and clicking Submit. We're going to try to answer as many as we can before the end of the session. Okay, now for our first question from the audience. Does IEC 61508 cover commercial vehicles up to 40 tons? Matthias?
Yes, thank you for that question. That's a very good question. So ISO 262 is actually an adaptation of the IEC 61508 standard. So it means it is based on IEC 61508. So as I mentioned during the presentation too, officially, this standard was not developed for commercial vehicles, but we can see a trend in the industry that is more and more used for commercial vehicles.
Excellent, thank you for that. And on to the next question from the audience. What kind of isolation fault can be detected with your isolation monitor product?
Yes, thank you, Matt. Very good question too. So we actually in our product use an active isolation monitoring technology. So you're able to detect symmetrical and unsymmetrical isolation errors with that. And as we also learned during the presentation, this is even possible if the high voltage bus is not energized.
Excellent, thank you for that. And to the audience, we are in the Q&A session, so please send us your questions. And while you're doing that, thinking of the questions you want to ask, I just want to point out on your screen, in the top right corner of the screen, there's a resource list. Within that list is a PDF copy of the slide presentation that was presented today, so you can download that and have it. You can also visit the website and also contact the Isabellenhütte team for more information. So please get in touch. We encourage you to continue the conversation. Okay, now back to the questions from the audience. Okay, here we go. Next question. Hello. Is there a comfortable PC configuration software available for the IVT-S? Matthias?
Yes, thank you also for that. So IVT-S, we didn't talk about this during this webinar, but this is one of our most frequently used products. And we actually have a video tutorial for IVT-S, so that's that I recommend very much on how to connect it to a PC. So we use Busmaster for that, which actually allows you, together with the CAN-DBC file of the IVT-S, to program IVT to get all the functionality working, program cycle times, CAN IDs, overcurrent thresholds, or whatever you want to program in this product. And there's also a guide how to hook it up to your PC with Busmaster. And we also will shortly release for the new product, the IVT 3rd generation. That's the product that I mentioned in this webinar at the end, which includes the isolation monitor and all this great new functionality like voltage sensing and so on, and has the ASIL rating. So we will also release videos for this product shortly. They should be on our website soon, how to configure these with Busmaster.
Very cool stuff. Thank you for that. That was a great question. Thank you for the person that sent that in. Okay, moving along to the next question from the audience. Okay, here we go. What ASILs rating do your products achieve?
Yes, so our newest product in our lineup, the IVT 3rd generation, has an ASIL C rating for the primary current sensing channel. And then the IVT 3.0 Pro, which also comes with the isolation monitoring and the voltage sensing, has an ASIL B rating on both of these functions. So it is ASIL-C for the primary current sensing and ASIL-B for the voltage sensing and the active isolation monitoring. And then the redundant secondary current sensing channel that this product offers has an ASIL-QM rating. So that can be used, for instance, to control a fuse, or if you need like an analog signal along with the CAN signal, then you can order this product with the redundant analog output channel.
Excellent. Thank you for that. And just want to remind the audience, we are in the Q&A session. You can still send us your questions. You can do that by typing it in the Q&A box on your screen and clicking submit. I'm going to try to answer everyone's questions today, but if we don't, for whatever reason, we will have an answer for you following the webinar. Okay, back to the list of questions. Wow, we have a lot of great questions in here. Okay, next question. You mentioned active isolation measurement has longer response times than the passive measurement methods. What response time can your product achieve?
Yeah, that's a very good question too. Thank you for that. So the response time of our active isolation measurement system varies between 5 seconds and 30 seconds. And why is that? This is because it depends on the Y capacitance of the measured system. So the capacitance between the high side and ground. So the higher the Y capacitance is, the longer the response time will be, but the maximum is 30 seconds.
Excellent, thank you for that. And next question from the audience. What is the max voltage you can do?
Yeah, this is a question that depends really a little bit on the product that we look at. But for the IVT third generation, this product has a galvanic isolation of 1,000 volts DC, basis isolation level. So that's the working voltage that we rated it for. It's rated for peak voltages of 6 kilovolts for transient over voltages. And the voltage sensing capability goes along with the actual voltage rating on the product. So it's also 1,000 volts. Having said that, though, we can, on a custom product basis, we can also achieve higher isolation voltages than that. Just as many of you are probably familiar with, the trend in the industry we saw, especially in the EV industry, was for a long time around 400 volts per packs. Now it's we see some trend towards 800 volt packs, so that's why we chose for the new product to rate it for 1,000 volts to accommodate those 400 and 800 volt systems. But as I said, on the custom basis, there's also higher ratings possible.
Very cool. Thank you for that. And thank you for that question. Okay, we have a lot of great questions coming in, so we're going to take a moment to just manage this a little bit. And while we're doing that, to the audience, if you do have any other questions, please continue to send them in. And we did receive a few questions, well, a few thank yous, so thank you. We're happy that you're here. We also received a few questions about whether or not the replay will be available, and indeed it will. The entire presentation today, including this Q&A session that we're currently in, will be available as a replay on the Global Spec site over the next 90 days. And it's the same link that you used today. You can use the same link to come back and watch the replay. Okay, back to the questions. Okay, let's see, what do we have? Okay, here's one. Okay, you showed a slide showing a high voltage battery circuit and voltage sensing points. You mentioned that active isolation measurement will be able to measure on a non-energized bus. So does that mean I will always get a measurement even if the relays are open?
Yes, that's a very good question too. Thank you for that. So yes, first of all, yes, with active isolation monitoring, you can monitor a non-energized bus. However, you don't necessarily get a valid reading for every possible combination of contactor states. So for example, if the relay on one side of the battery is closed and on the other side of the battery is open, you will get an undefined state of your system. and hence you will not get any isolation reading. If all contactors are open, on the other hand, you will get valid readings for the link side and the pack side isolation readings, but not for the total isolation readings. And then obviously, if all contactors are closed, the system is operational and you will get the total isolation readings.
Excellent, thank you for that. And next question from the audience. What is the cycle reporting time for isolation monitoring?
So the cycle time for isolation monitoring in our product is set by standard to 100 milliseconds. It obviously depends a little bit on the product that you're looking at, but we basically chose for our product to offer a cycle time of 100 milliseconds.
Great, thank you for that. And again, just want to remind the audience, we are still in the Q&A session. You can enter your question in the Q&A box and click submit. We have our expert online and ready to provide your answer. Okay, we have a lot of great questions in here. And let's see what's next. Okay, here we are. Also referring to the voltage sensing point slide, what happens if I connect the isolation monitor to a different position in the system? Is this possible, and how will this affect the isolation monitor functionality?
Yes, good question here too. So this depends on the configuration possibilities of your isolation monitor, obviously. So the module that we offer allows to position the monitor either on the positive or a negative leg of the battery to get valid readings. So it is also capable to read current bidirectional. So you can either use it on the plus side or the minus side of the battery. However, I mean, you know, for other isolation monitors out there, they might be configured for use in different locations. But with the system that we looked at, you have those two possibilities. Either place it on the plus side of the battery, and then your first sensing point would correspondingly be on the minus side of the battery, or if you place it on the minus side of the battery, your first voltage sensing point would be on the plus side.
Excellent, thank you for that. And we still have some more questions in the queue, so we're going to keep it going. Here's a question that actually came in during the presentation, Matthias, so hopefully you can remember the reference here. It's the question is, on the slide with the high voltage circuit, what do the green dots stand for?
Yep, thank you for that. I think I know which slide this refers to. So that was also the slide that showed the high voltage circuit. And I don't know if you remember, but we showed the red dots as the mandatory voltage sensing points for your isolation monitor to work, and there were like 3 green dots on the slide too. And this basically just refers to the other 3 voltage sensing channels that our product offers. So with the IVT 3rd generation Pro product, you get up to 6 high voltage sensing channels, and 3 of them have to be used in defined spots for the isolation monitoring to work properly, and that's there were the red dots on this slide. And then there were 3 green dots, and these are additional high voltage sensing channels that can be used freely by the customer. So you can basically use that to monitor other relays, you know, or use it in your pre-charge circuit or wherever you have the need for additional voltage sensing points.
Excellent, thank you for that. Okay, we have a few more questions to go through. We do have some new ones coming in, so if you can give us a moment just to take a look at the queue and manage this a bit. And while you're doing that, audience, if you do have any additional questions, please send them in. We'd love to hear from you. Okay, next question. Okay, here it is. What happens with the isolation monitor when the vehicle is being charged?
Yes, thank you. Also, that is a good question. So normally, the charging station has its own isolation monitor. if we talk about DC fast charging, so for AC wall boxes, the onboard current sensing of the vehicle usually, or the onboard isolation monitor usually does overtakes this task. But if we talk about DC fast charging, the DC fast charger usually have an isolation monitoring system. So in that case, the charging station system can interfere with the vehicle's isolation monitor. So the vehicle's isolation monitor should be disabled during charging. I have to say, though, this has to be evaluated case by case and based on the system that is used. So you really have to look at that system by system.
Excellent. Thank you for that. And we have time for one or two more questions. So let's try to slide a couple more in. Okay, here it is. Here's our next question. Is your isolation monitor product available?
Yeah, that is a good question too. Thank you. So we currently have B samples available of our IVT 3.0 Pro product. And again, as a reminder, so the Pro version includes the isolation monitoring functionality and the voltage sensing functionality and has the full ASIL ratings on all these functions. And so B samples, what does that mean? So these are functional prototypes that haven't gone through validation yet. So this validation still needs to be done. And for the Pro version, we actually expect C samples in, so those are products that have the product validation completed, but process validation is not fully completed. So we expect these in the first quarter of 2023. We have to consider a full year for validation because of this ISO 26262 functional safety standard that basically requires very extensive validation and documentation. And the SOP is currently scheduled for fourth quarter 2023. However, the base version of IVT 3.0, which still gives you the ASIL C-rated current sensing and the option for an analog secondary current sensing output. This will go into production already by third quarter of 2022, so third quarter next year. So that will be available significantly sooner.
Excellent. Thank you for that. And to the audience, again, on your screen, you can always visit the website or contact us for any more information about that or anything related. Okay, great. We're getting to the end, but I think we have time for one or two more questions. So here is our next question. What are the accuracy ratings for the IVT-3.0?
Yes, that's a good question too. So our products are fully temperature compensated for lifetime. So the products have never to be reconfigured or revalidated by the customer. So the temperature compensation is over lifetime, and we rate our IVT 3.0 product for 0.1% initial accuracy. What does initial accuracy mean? Initial accuracy means that we basically make sure with our end-of-line quality control that no product leaves our factory with an accuracy less than 0.1% of reading. And we also, that's also important, we also rate all our products with accuracy of reading. Means like, you know, if no matter if you measure 100 amps or 1,000 amps, the accuracy will always be 0.1% out of that reading. A lot of other manufacturers of current sensing products rate by range. So that means you get like whatever the maximum range is of accuracy out of every reading. So we don't do rate our products like that. And the total accuracy, we do a total accuracy rating too. That is the accuracy over lifetime. So we have the initial accuracy, which is how the products leave the factory. And then we have the over lifetime accuracy rating, which is 0.4% total accuracy over lifetime. So the accuracy will never get worse than 0.4% for the nominal current and voltage sensing ranges of these products, and even into the first stage of overcurrent sensing range, which goes, the normal range goes up to 1,000 amp, and the first stage of overcurrent sensing range goes up to 1,500 amps. So the accuracy up to 1,500 amps is still 0.4% total accuracy. And then, as I'm already talking about accuracy, so the total sensing range of the new IVT 3.0 is 4,000 amps. And even in overcurrent range up to 4,000 amps, the total accuracy will never go below 1%, which, by the way, is also a big improvement over the predecessor product, IVTS.
That's amazing. Thank you for that. It's very obvious why you're a leader in the industry. Okay, folks, we're nearing the end. However, we have time for one last question, and so here it is. What is the sensing range of your isolation monitoring product?
Yes, good question. So our active isolation monitoring system will sense up to 50 mega ohms. So that's the max range, with a total deviation of 30% for measurements larger than 5 mega ohms, and 25% for measurements between 100 kilo ohms and 5 mega ohms, and 30 kilo ohms for measurements below 100 kilo ohms.
Excellent. Thank you for that. And that was our last question, so we are going to wrap things up right there. So Matthias, thank you so much for that great presentation and also taking the time to answer some audience questions. I'd like to also thank our audience members for being part of this webinar event. As mentioned, you will receive an email with a link to the on-demand version of this presentation, so you can come back and watch it again or share it with your colleagues. And lastly, please take a moment to complete a survey, which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.